It's my pleasure to see you all here. And okay, we don't speak about those who are not here. It is my particular pleasure to introduce Jakob Rehof. He was here already last year, despite the fact that he was not visible so much.
He was visible but not present.
He was present but not visible. But this year it is much better. So it's always a pleasure to listen to Jakob. And today, but he's a full professor. Even if he's not drunk, he's full professor. Okay. He's a full professor of informatics in Dortmund University. He's also head of the department of Fraunhofer Institute for very long, and he has done so many other things which I don't want to speak about now. Today he will speak about a very interesting topic. It concerns modeling, namely he generates models, simulation models from components, and he does it in an industrial environment. So please, Jakob.
Well, thanks a lot for inviting me again this year. Thanks, Frank. Thanks, Wolfgang. Thanks to the organizers. It's a real pleasure to be able to speak in front of the audience here in presence. Last year, as they were kind of getting at, I had to give a talk from my rooms where I was isolated because of the stupid problem back then. Okay, so we don't have that now, and I'm really pleased to speak in front of you. So I think I have about 50 minutes slot. I'll try to make it a little bit shorter than that because I really wanted to discuss this topic with you, and so I'm really interested in your feedback. So I'll try to reserve some time for that and just look at the box here. The topic is kind of the same line of work that I was trying to present last year. So if some of you listen very carefully, you will see some repetition, but I guess we'll have to live with that. But then I will try to spin it along sort of a line that has been picking up over the past year. So it's not just old stuff that I'll be talking about. I'm also pleased here to mention that a PhD student of mine, whom I call Connie, his real name is Constantine Chaumet, has been helping me greatly with these slides, and you will see why, because in particular there are some animated parts that I could never have done myself. Connie is a PhD student in our Arduino colleague, and he's crazy about robots, and he's particularly crazy about robotic arms, which is kind of a fascinating subject on its own, you know. And this is something you will see in this talk manifested in several places. With that, let me just say what I will do. I will first say a little bit, not as much as I tried to do last year. I won't say too much about the background. I want to get more into some of the applications. But I will say a few words about the background, and you may get a little bit of repetition there from last year. The CLS framework is this kind of tool that we've been developing over several years, and which is in action here, and which we're extending also towards capturing more and more of these kind of use cases that kind of have this thing in common, that they come out of sort of classical engineering. So it's about bringing software engineering into the space of classical engineering, trying to say, could we not finally help these sort of classical thing-oriented engineers be smarter about how they deal with software? And I will in particular talk about two use cases, one coming from the motion planning space, and one which is a new one I've been doing with developing with Connie over the past months, year, is to integrate our synthesis framework. I will already say it now. This is a program synthesis framework, and to integrate that with CAD synthesis, with CAD design. Okay, so to the left, I have this CLS thing, combinatorial logic synthesizer. What is it? It's essentially a framework for automatically putting together components guided by type theoretic interfaces. Okay? So you have components, Those components have interfaces. Those interfaces are types in a pumped up type language, which is theoretically very interesting, very well understood. It's called the intersection type system. It has a lot of fascinating theoretical properties. I'll not touch on those. We're trying to use it in practice here. Our components we think of as combinators, which means essentially typed functions. And you may ask, well, is that then here an exercise in functional programming? The short answer is no, it's not, because those functions might be meta functions that wrap code in other languages than some functional language. We also now have an implementation of the CLS framework in Python, which allows you to use some of the freedoms of Python as well, which is actually important in the context of the kinds of applications that we're talking about now. A lot of engineering today is going on in Python. The basic sort of synthesis pipeline of the CLS framework, CLS again stands for Combinatorial Logic Synthesizer, is that basically it solves the so-called inhabitation problem in type theory. That is, you've got a bunch of functions with types, and you ask the question, is it possible to find a composition of those given functions such that a given goal type becomes realized, that is, such that that function composition has the goal type. Okay. And that's called the inhabitation problem in type theory. And what part of the background for the CLS framework is that we spent a number of years, about 10 to 12 years ago, started back then, developing new algorithms for various fragments and various forms of these inhabitation problems. What comes out of that is a tree grammar of all possible solutions. An applicative solution, that is, a solution consistent of functional applications, is a tree. Syntactically speaking, is a tree, right? If you have a bunch of functions and you apply them to each other, what you get syntactically is a tree structure. That's a very nice feature because trees are sort of well understood, well behaved, mathematically understandable structures. And so what comes out of a synthesis request is actually a tree grammar, which recognizes exactly the set of solutions. Now, important to note here is that there might be multiple solutions to a request. For example, because there might be multiple functions having the same type in the repository, that is in the input collection of functions relative to which the synthesis is done. Okay? So it's a non-deterministic process, and there may be multiple solutions, and that's actually a good thing for the kind of application that I'm interested in. You'll understand that later. Once you have this grammar, you can start talking about enumerating the individual terms. Those are then the individual function applications that are members of the solution set. And it's an interesting problem to think about how to do this. I'll talk about that at the end. And then there comes an interpretive phase where these abstract trees consisting of function symbols that get applied to each other are interpreted in some structure. That means there could be very different things. It could be code in some other language than the language of the functions, those functions in the repository, because, as I said, those functions might just be wrappers for meta functions that generate code in some other language, for example, Java or Python or whatever. It could also generate PDF documents if that's what you want, like documentation. It could generate XML files and so on and so forth. All of these examples are things that we've actually done in practical applications of the framework. Here's just a pictorial view of the basic synthesis pipeline. You've got a component repository in the set. Those are functions, possibly meta functions. They have types. There's a goal type which says, can you construct out of these components? Is it possible to construct one or more compositions of those functions with the given goal type? CLS itself solves this inhabitation problem and generates a grammar of all possible solutions, which are combinatorial trees that then can get interpreted into actual programs which we can then execute. Okay, so this is the basic pipeline of the whole thing. And I just want to hope that you will have this pipeline sort of in mind. In the applications I'll be talking about now, This basic pipeline gets extended with statistical and learning features. In particular, we're going to use a particular tool called Hypermapper 2.0, which you can think of as something that produces, in our application, it's actually a statistical Bayesian component written by other people, and I'll cite them. The citation will come up later. And what it's able to do is it's able to walk around a complicated parameter space and essentially find Pareto fronts in that parameter space. And where the optimization function may not be known, so it may be used for black box optimization problems. And that's also where the learning facilities of the hypermapper component may come in. The picture here, this is a particular set of measurements that were fed into the hypermapper and led to the identification of a certain Pareto front. To tie it up with the main loop, with the main pipeline here, you see, the moment you use CLS to generate possibly multiple solutions, what you can do then is you can feed those solutions into various forms of measurements. Either you execute, those programs, and you might want to choose the one that runs fastest. So there's a lot of sort of basic philosophy that went into CLS from the beginning, where I said I don't want to try to do synthesis by specifying everything up front. For example, runtime performance characteristics of generated programs is not something I would like to try to a priori specify prior to synthesis. So I like to work with like this possibility of having like a sort of division of work, where you use type structure to basically specify what are basically well-formed solutions, and you use this extended type language, intersection type, to capture that. There's a whole wonderful theory to that. I said I don't have time to go into that, but you see these intersection types appearing here.
Jakob, where do the samples come from?
What?
Where do the samples come from in the figure?
So these samples, actually, the samples here refer to sample-based motion plans. Those are not samples that we produce, but they are the programs that we are going to generate in one of the applications. So the first application I'll talk about is the automatic generation or synthesis of sampling-based motion plans, which can be used to control robots and robotic arms, for example. Okay. So, but once we have these programs, this box here is now just a placeholder for multiple programs that are solutions to our synthesis problems. What we can then do is, of course, we can pipe those solutions into various measurement instruments, like execution, measuring performance, or we can feed them into test suites to see if they satisfy certain testable requirements, or we could do other measurements. In some of the applications that I'll talk about, these programs are actually simulation models. They're simulation models of something physical, typically some engineering problem. They may be simulation models or other kinds of models of physical nature, for example, robotic arms moving. So you'll see that. And so the basic idea with the CLS idea here is that we try to be smart about not putting together things that are completely meaningless up front, but we defer to a later stage to measure on the candidates that we're generating, and we're well prepared to generate a superset of solutions that can actually be used in the end, because we're going to filter them away after the fact, after they're generated. And so that's also what provides the basic opportunity for kicking in things like learning instruments in this loop, to create a loop. So if I have my solution space, I can execute and measure on the solution candidates. I get result vectors out of that if it's a numerical problem that I'm looking at. I can then feed those result vectors into this hypermapper. This hypermapper can now start driving a synthesis loop, because the hypermapper might actually know of some kind of parameter space to which these result vectors apply. And so the hypermapper will start walking according to some Bayesian logic or some other logic. It's going to walk around this parameter space, and it's going to choose a new configuration for certain parts of the repository that might be responsible for generating various kinds of results for various, that might be responsible. So you configure certain components in the repository in a different way, and in the loop you are now able to see the effect of that configuration. Okay, so you have kind of like really a framework for iterative and generative optimization and learning.
Jakob,
yeah, sure.
Who decides when to stop? I'm asking this because in quantum computing there are variations in quantum algorithms. You have an ansatz in the quantum computer, you sample, you measure, you optimize, you turn new parameters.
Yeah.
So the loop in
Yeah.
each sequence seems to be the same.
Yeah.
So who decides? The hyperparameter decides whether certain criteria?
It could. I mean, you can, the hypermapper is highly configurable. So you can tell the hypermapper to stop at a certain point.
Based on the criteria.
Yeah. So it's one of the strengths of the hypermapper in particular. I mean, I should say, this box here is just, in my mind, methodologically, it's just a placeholder for, hundreds of other kinds of learning mechanisms you could think of putting in here. But particularly the hypermapper, I'll say a little bit more about it later, so I won't do now, but it's been particularly useful for the kinds of applications that we're interested in. Your question is the sort of thing that I'd like to maybe have a deeper discussion with you later, which we were trying to do last year, but for various reasons it didn't fly. Okay, so the first application is in motion planning. And so this is essentially about finding some sort of workable compromise between various performance metrics. When you're talking about motion planning, that's a multi-objective optimization problem, because some plans might be fast, but then they might not be sufficiently complicated to avoid certain obstacles. And the idea in particular of sampling-based motion planning is that you've got various kinds of sampling strategies and algorithms that you can put into sampling-based motion planning. So there's really what I call an algorithmic family. That's something I'm very interested in. Algorithmic families. That is, algorithms that are slightly different. They try to do the same sort of thing, but they work with different kinds of strategies, and you may be able to tune them by parameter tuning them, and so on and so forth. And that's the kind of stuff that we're going to be concerned with here. Here's a little bit more detail on what the loop sort of looks like. In that particular case, I will just single out a few things. Here, the OMP-Elko templates and configuration is important to me because it's an instance of something I like to do, maybe to take existing libraries and use them as the basis for the component repository. Okay, so the idea is not that we're going to invent these components ourselves. I like to go out and find existing components, then wrap them in a suitable way such that they get accessible for CLS, and then we start this generate and test plane with these components. In our case, for this application, there's this open motion planning library, which is used by a lot of people doing motion planning research, and we use that as the basis for the repository that we're looking at here. You see also here that the hypermapper 2.0 is here driving a loop where the results that it gets from the various experiments coming out of CLS that generated some solution candidates, and they were executed in multiple program instances. I mean, they were executed, either different solutions were executed, or as well, different parameter settings for single ones of those solutions were automatically executed and measured on, and that then results in these result vectors coming back to the hypermapper, which then starts driving a new instance of the loop by making its step in its parameter space and trying out a new point in that vector space, that giving rise to a new configuration that feeds into the repository at various points. I mean, we might have motion planners sitting there that have numerical parameter vectors that we can tune, for example, or for a particular kind of step that the hypermapper makes, maybe the hypermapper chooses solutions from a particular sampling strategy, and then certain parts of the repository become obsolete, and the arrow out of the hypermapper in that case would actually remove from consideration, the useless components that have no relevance for this loop instance. And so that's an optimization of the loop. So we're trying to be smart about what we're looking at when we generate these things, because after all, there's also a computational cost associated with the generating. So, yeah,
question.
yeah.
If you use third-party components, how do you know what they do and how to use them?
Yeah, let me put it this way. The more you know about that, the better the results will be faster. Okay? But I mean, if you don't, you could try things out. I mean, there's nothing that would prevent you, in particular in the Python instance, you don't even have to know the types. Okay? Which would be a fairly basic form of ignorance. Okay? But I mean, in principle, actually machine learning people like to operate like this. They just generate something. And they have no idea what types are, they have no idea what logical well-formedness is. They just generate willy-nilly things and then they measure them. Actually, there's a very spectacular case of that. I have that, if I have time at the end, there was just a paper by some Google researchers using AlphaGo to use synthesis, forms of synthesis combined with reinforcement learning to automatically identify machine code, strings of machine code instructions that can optimize the searching algorithms. It's a pretty fascinating project, and it was published in Nature in just a couple of months ago.
In pragmatic, I've been raised with the Danish method for formal semantics.
Say that again, please.
I've been raised with the Danish method for formal semantics, EDM.
With the Danish Bjørn?
Yes.
Yes. So I will not argue against that this morning. Okay. So it's multi-objective, and in the context of these applications that I talk about here, the main function of the hypermapper will be to compute a Pareto front of solutions. This is sort of what the hypermapper looks like inside. If you open it up, here's the reference. I can recommend this paper. Udo Kutum is a fairly renowned colleague from MIT. And this group here, they specifically work on the automatic design space exploration for systems design. So they're computer scientists, okay? And so it contains a number of technologies that I have listed here. I'm not going to go into that, just for your reference. In the case that we're going to be looking at, we are dealing with a design space for planning programs. So there are different kinds of planning algorithms, there are different kinds of sampling algorithms. We're talking about sampling-based motion planning. So motion plans will be sampling the space to understand the geometry of the space and how the plan interacts with that, because it's too costly to compute these plans on some sort of completely specified space. So you do sampling strategies, there are different strategies, different algorithms, there are different kinds of so-called state validators that you can put in to the algorithm that looks to see if what you reach, if you make a move, is actually a valid state in the system, and motion validation is also a part of it. Just think of these things as various sort of dimensions of variation that you can have in this space, in this algorithmic family, okay? And you can also think of each of these as having further parameters like speed parameters that talk about how fast the sampling has to happen, and so on and so forth. And so a solution in this case may actually be some kind of trajectory that moves through some sort of space that might have obstacles in it, for example. Okay. And so, yes, basically, again here, derivative-free optimization is a key word, which is important to the hypermapping, the hypermapper kinds of applications that we're targeting. We're talking typically about optimization problems that may have, for example, important discrete parts to it, where you don't have a differentiable function as a different function. So here's the first sort of application scenario, which I'd like to just illustrate with some of Connie's great pictures. So we had done some work to automatically generate these sampling-based motion plans, and there's a paper cited about that, which we published last year. That was just about generating motion plans, executing them, and using the hypermapper to find Pareto optimal solutions for those, okay? The next step that we did was to actually tie it up with robotics. Now, these motion plans get fed into some sort of robotic design, like this arm. And now these motion plans are designed to actually control the movement of these robotic arms. My second application scenario today will be how to use synthesis integrated with a CAD tool to actually build these robotic arms, okay? Connie did actually a lot of experiments with also using a 3D printer to print out various prototypical forms of these arms. That was also a lot of fun. But actually then we took the next step and wanted to really connect it with serious engineering CAD tool. Okay, but the first thing is we generate these sampling-based motion plans, and we're now going to use it to try to consider just automatically explore multiple sort of planning situations vis-a-vis different robotic arms, and try to automatically explore the design space, trying to figure out which motion plans and which robotic arms, which combinations are good in given situations. This is sort of the setup, and also in this case we can compute Pareto functions using the hypermapper. And in the little movie that I'll show you now, there's a reference to different kinds of figures. Those are the figures that are referenced here. Those are different measurements of candidate solution motion plans combined with robotic arms. Let me see if I can start this video here to get that going. So this is now a video that should be running now. I hope that it's dynamically developing. Yes, it is. So we now see this is a robotic arm with 4 degrees of freedom that is placed in a cylinder, and there's a part of the cylinder cut out. And what you see now is a simulation which is co-generated with the generation of the motion plan and the robotic arm design, okay? To see how that design works with that sort of motion plan. Then we put it into a different kind of uniform valid state and uniform space that refer to different categories of sampling algorithms. And the nice thing here is we can actually then explore, we can see what comes out of the process. And here you're seeing a different sort of challenge now. These different colored arms, they correspond to different solutions, okay? There are different motion plans controlling the same type of arm in each picture. And
But the last video didn't show all the potential arms.
We just took some. These are just examples. This one is sort of visually pleasing, I think. It's just a nice picture. And now the robotic arm is operating inside some sort of semi. And so. That's a 10, that's now a 10 degrees of freedom robotic arm. This robotic arm is more complex than some of the ones you saw before. Now you see here the variation in robotic arms. This one is trying to get into some kind of cylindrical structure. Okay, so that's just to show you what comes out of that. Let me see how I go on here. I might have to actually stop Yeah, so moving on. We also used this case study to study things that statisticians like to do, for example, talking about model transfer. That's sort of the basic question in a lot of statistical scenarios, and also learning scenarios. If you learn something in one kind of scenario, the question becomes, well, is the learning mechanism transferable to other kinds of scenarios? And this is something that I actually thought that we should use CLS somewhat more to explore, because I think that the idea of using synthesis to generate, for example, different motion plans is fine, but you should really combine it then with automatic generation of various kinds of scenarios, that is, various kinds of geometrical configurations in which these plans play out. Then it becomes also a kind of automatic testing, if you will. But the question then, from a statistical point of view, becomes how transferable are sort of the models that get learned in these experiments. And we were able to actually transfer some of the model in a fairly okay way, but the models that we learned on, it seemed to work pretty well in the cases where we were generating motion plans to move through space. I mean, think of it controlling like a moving object, a moving robot, for example, floor transportation robot moving on the floor through a room, and there would be obstacles in the room, and how well do learned solutions transfer in that space. That worked out okay, fairly well. It did not, however, work out very well when we came to the application that I showed you, which was about those robotic arms. Because apparently there are too many specific variations on these robotic arms. They're just too inherently different for transferability to be easy, at least. I would not exclude that it could be done. But this is just an example of the kind of question that we can sort of answer by having this kind of automated experimental loop. You know, I mean, my dream is to one day be able to really show that we could do experiments that could not possibly have been done by hand. I think some of the scenarios we've done already have that characteristic. I mean, you could not possibly realistically have reached that number of coverage on the design space by purely manual means. So that was the first application. The second application is now where Connie really kicked in, because he started developing, and he's still working on that, a kind of integration between synthesis by CLS and CAD tools. So the idea here is that we want to use synthesis to try to relieve classical engineers from repeating the same basic tasks over and over and over again. And doing that by sort of auto-generating assemblies, and thereby improving creativity by freeing up time for really creative tasks while taking out of the equation time spent on idiotic tasks like repeating things you've already done, or doing other kinds of things that could actually be automated. And so this work is ongoing. This is something we just submitted something to ASE on this book. And so on the topic of repetition, here is Connie's kind of motivational blurb. Products nowadays are really one-offs, but usually part of larger product lines. Members usually similar, share many identical modular parts. Repetitive tasks are still very much required, even in, top-notch modern CAD software. And the idea of using CLS to do CAD assembly synthesis is to try to get rid of that repetition and explore the design space by automation. Okay, and so here are a couple of examples of what repetition might mean. I mean, he's saying here, that if you want to create something like this or create something like this from his robotic arm space here, he's kind of listing how many screws you have to put in and how many clicks you have to perform in the CAD software, you know, just to put this thing together. And these are examples of operations that will be automated, essentially. Okay, and so what he did was he created an add-in for a tool called Fusion 360, which is a CAD tool which is used in a lot of research, but is also increasingly used in industry, in particular in small to medium-sized companies. And he created kind of this CLS plugin for Fusion 360, which allows you to manage type structures and type-based hierarchies with subtyping relations that implement taxonomic structures. I'll give you an example of what that means, why that's important here. That's integrated, so that what that really means at a high level is that he integrated into Fusion 360 a certain set of operations that are useful for configuring, for example, the CLS component repository and doing other kind of configuration tasks that are useful on components in this context, like annotating geometrical features or forms, and also for, at the other end, to request certain products and to choose parameter settings and make your choices for your solutions. Okay. So this taxonomy editor allows you to build sort of classical taxonomic structure that pertain to the kind of objects that you're interested in this case, to do type annotations on the repository, and also to automate firing up CLS and bringing in the solutions back into the CAD tool so that you automatically get them visualized and so that you can manipulate them back afterwards in the CAD tool. And there's a movie about that as well, which I think will come now. Let me just see what I need to do to activate it. Yeah, so what you see here is actually him working with his Fusion 360 tool extension that uses CLS. What is going on here, I don't have time and probably also not the understanding to explain every detail of what's going on here, but what's basically going on here is that now he's building up various forms of robotic arm bases. They're going to hold the robotic arm. That's what they're going to stand in. And now he's starting to automatically synthesize. This is the synthesizer working here. So the CLS synthesis is now, what you see is it building a certain kind of solution, okay, that then gets automatically fed into the CAD tool. And I mean, what you have to understand is that in a round of work like this, he may be building hundreds or even thousands of these solutions. We're looking at one particular.
Do I get it right, even including the screws?
Yeah. So it actually really gets assembled according to the CAD model. Now, of course, one thing that's fascinating is that we immediately take advantage then of the physical mathematical CAD model that's in there. Now, there's a lot of physics being modeled, coming for free. That is, what you just saw at the end was that he was then starting to manipulate the robotic arm. And you saw that when he was making one movement up here, it kind of got automatically, coupled up with a movement closer to the base. That's the whole mathematical physical model that's inside that CAD tool that's at work here. So I just find it fascinating by putting these things together. And there's a lot of there's a lot of value add that sort of comes in extra. Okay, so that was that. Let me see if I can go on. Beyond that, yeah. So Another kind of application that I know Connie is interested in is to try to get rid of suboptimal parts. So his observation here is that in complex situations, in complex engineering, with complex engineering objects, you may actually have engineers using suboptimal parts just because it's always been part of how things were done, or because it's not even understood completely. Nobody has really gone through every possible detail of what is actually getting in there and what other possibilities are there. Here he has like two different kind of servo motors compared, and what he's saying is that he would like to use the CLS-based hypermapper powered loop to try to learn, for example, which kinds of components contribute to good solutions and which don't. And in particular, that could lead you to, for example, automatically identifying components, now components in the sense of physical components, that you shouldn't be using if you want to reach certain goals. Okay, the learned model can be utilized to improve the repository of parts. Okay, so that's the basic idea. And so those were the two kind of scenarios I'd like to show you today, and because I would like to have a brief discussion with you if possible, I just wanted to point out that there's a lot of opportunities for further work. If you look at the basic extension, the basic CLS pipeline, there are kind of 3 points where you can immediately think of powering up the framework. That's not even the loop, that's just a synthesis pipeline. We've already done a lot of work to do that. The automatic ways of getting those components in a semi-automatic way at least is important. I mean, the largest upfront cost that you have in applying this whole methodology is getting the initial repository. Now, in a lot of cases, we don't write those components ourselves up front. I already said that. We take them from existing libraries, or we even engineer them out of existing complex simulation models. We also did a project where we did that. So we took an existing highly complex simulation model, and then we engineered the components out of it, generalized those components, wrapped them for CLS, and all of a sudden we had not just the ability to generate that given solution, but we could generate a whole family of similar solutions that, however, had variations in it. Okay. In the middle here, this grammar, this tree grammar that comes out, carries a lot of opportunity for interesting work, some of which we did. We had a theory paper on some new results on algorithms for filtering tree grammars according to re-ranking systems, which was theoretically interesting actually, but it also turned out to be interesting for some practice. That's why we did it. And at the end here, there's this opportunity for putting in various kinds of measurements, in particular statistical and learning instruments, as I was already saying. And so this is now my menu for future work and ongoing work. This one is something I think about a lot. This is enumerating the candidates, various strategies for enumerating the space of solutions that we generate. What I really want to be able to do there is to conduct controlled experiments. The way I think about that is, if I take a tree, that's a solution. I could put holes in the tree, and then I could ask, which things can I put into those holes so that the members are still members, the resulting trees are still members of the solution space. I could try to automate that process. Then I have a notion of what is the next step in the solution, starting from some tree structure in the solution space. That will give me access to reinforcement learning methods, for example, because there you need to have the notion of what is the next move in the game. And so I think I can tell what the game would be. The solution enumeration game will bring us in contact with that kind of technology. And also synthesis of neural net architectures is also an obvious kind of thing to be looking at. We've got these neural nets. They get experimentally used in some context, make experiments, fantastic things, but as you know, some of the problem is that what happened if I took another net architecture? And we want to use this technology to contribute towards scaling up that kind of experimental work to try to figure out what architectures are particularly good or particularly bad, also doing things like hyperparameter tuning on there. Okay, so with that I will stop.
Excuse me, the second last bullet.
Yeah.
This is not for each and every algorithm.
No. This is
in this domain.
Yeah. No. This is
Yep.
This is very dependent on not every algorithm, but some algorithms come in interesting families. Okay, and so it's very interesting to try to discover natural algorithmic families. So algorithms for moving things, for motion planning, they may come in natural families. That was one example, but there are many others. There's something called the A-star family of motion planning algorithms as well. And I have an ongoing thing about having solutions generated for moving through various kinds of mazes, where that algorithmic family comes into play.
Here, configuration means something like hyperparameter?
Yeah,
okay.
Yeah. Or simply, it could be hyperparameters, or it could be like, for example, setting the speed parameter for a motor. Anything like, but it's typical numerical stuff. And so one thing that I'm thinking a lot about as well is how to really, in a systematic way, unify into CLS essentially numerical vector spaces, I mean, like really numerical stuff. This is where also the conversation I wanted to have with you, but which we might be able to continue at some point, where I would like to see if this sort of technology could play a role in just scaling up some of the experimental work that might be of interest in the space that you'll be looking at in quantum computing, for example. You see what I'm saying? What I have found is I have found at least this technology to be amazingly applicable in a relatively short period of time by my people. I mean, of course, they have studied the area, they spent some time working at CLS and understanding what it is. I'm not saying it's someone coming in from the street, but still, we have by now done, I would say, I mean, I'm very satisfied, at least, with the number of different projects we've been able to carry out in a meaningful way using this technology. So that's something that keeps motivating me a lot, actually. You know, we could walk into this motion-based sampling, this sampling-based motion planning space in a reasonable amount of time and have results that we could publish there, right? Although none of us are experts in that area. And so I'm hoping a bit that the same will happen with the CAD application. I'm not quite there yet, but almost.
Perfect.
So I assume there may be some questions to Jakob.
I have a couple of questions.
Yes, you don't have another one?
No.
Your answer. Yeah, okay.
I would be interested if, that was amazing, thank you for the presentation. If you have also built the real robotic arm, if there is a feedback loop from the real robotic arm to your simulation, because then you can even improve the simulation.
Yeah, absolutely. What was said here, I don't know if everybody could hear it. How about integrating this with actually building an actual robotic arm and see how that behaves and then have that feedback into the simulation model? That's exactly one of the next steps we want to make. Yeah. His office is actually full of actual robotic arms. And a lot of these things he actually builds. But you want to automate that, and you want experiments from the physical world to feed back into fine-tuning your simulation models and the other models that go into the generation of these things. So absolutely.
Okay, another question? This session was so fantastic, so nobody else.
We already had some.
Everybody wants a coffee? Okay, so in this case we thank you again, Jakob.
Das ist gut. Alles verstanden. Das alleine nehme ich als
schöner Vortrag. Das ist Ihr Privathaus.
Das ist es, ja genau. Aber Sie können es gerne bleiben. Ich bitte Sie darum, nicht nachher, dass ich vergesse, was ich mache.
Ja, das ist das Problem. Gibt es hier einen Stöpsel?
Der geht rein und dann ist hier on. Okay, das war der Punkt.
Ich kenne das Problem mit den
Ja, das ist
deswegen nehme ich meinen Adapter immer so gerne.
Ja.
Ja.
Das ist wie die iPhone-Chargers im Hotel sind.
Ja.
Ich hasse das, wenn ich dann im Flieger sitze.
Da war doch aber die sind teuer.
Ja, das ist genau.
Genau, ganz richtig. Du bist uns, das ist für dich die Station an die Klasse. Ja, das nennt man ja alles. Aber es kostet was gratis Geld. Und da hast du heute bekommen hast, das brauchst du nicht. Wir haben ihn und Sebastian mitgeben. Das ist Sebastian diesen Wort, ja, das ist super. Ich weiß es gar nicht. Okay? Du, aber ich mache jetzt wieder Schluss, denn ich bin jetzt zum Schluss. Okay? Naja, das ist bei allen Vorträgen, ganz in Ordnung. Ist echt, wenn mich interessiert, ist echt auch. Ja? Ja? Wir sind am Flughafen, gell? Yes,
I was in the back, and I thought, I'm faced to be closer.
Yeah, we have team at
See your slides.
you know,